This video is brought to you by mywayteaching.com.
Next concept is polarity of bonds. Okay, in that polarity of bonds there are the two types, that is polarity means non-polar covalent bonds and polar covalent bonds. Okay, and I will explain you what is mean by what is dipole moment and all. Okay, so here before going to that I will explain you when the covalent bond is formed between the two similar atoms, between the two similar atoms, when the covalent bond is formed. Example for this, H2O2 and Cl2 and etc. So okay, so here when there is a see, comparing to this HH, the shared pair of electrons are equally attracted by these two hydrogen because they are of similar atoms, two similar atoms. So as a result, electron pair is situated exactly between the two identical nuclei. The bond is formed, that is known as non-polar covalent bond. Non-polar, this is called non-polar covalent bond. Okay, like that. There is also when coming to the different atoms, okay, hydrogen and fluorine, in between that when there is a bond is formed. Okay, so here towards electrons will be attracted more towards the fluorine because the fluorine having higher electronegativity negativity high electronegativity comparing to the which is having a greater than that of the hydrogen, so that it will be attracted towards fluorine. This is known as non-polar, this is known as polar covalent bond. Okay, so this is about the polar covalent, non-polar covalent bond and polar covalent bond. Okay, and I will explain you what do you mean by dipole. What is a dipole moment, which can be defined as the product of the magnitude of the charge and the distance of the okay, and charge and the distance between the centers of the positive and negative charge. Okay, so this is the it is this is called dipole moment. It can be expressed in dB units, and the 1 dB is 1 dipole is equal to 3.33564 × 10⁻13 coulomb meter. So this is the coulomb, where m is the meter. Okay, and the next thing is dipole moment. We how we can represent the dipole moment. Okay, so here consider H and F. Okay, so as in the case of vector quantity, we are assuming that the tail in the vector, okay, in the vector quantity, the tail is the on the negative and this is the positive. Correct, positive center, this is negative center. But in chemistry, so this is not in the chemistry. What happens in the presence of a dipole moment is represented by the, this is represented by the arrow. Okay, Lewis dot structure of the molecule, the cross is on positive and the uh, positive end, and the arrowhead is on negative end. So this is the arrowhead is negative end and this is the positive end. Okay, in the case of chemistry, so this is the cross and this is the arrow, like that. This is the positive end, this is the negative end. Okay, so this arrow symbolizes the direction of the shift of electron density in the molecule. Okay, this is representing a direction of the shift of electron density in the molecule. Okay, so this is about the dipole moment. Next, I will write down one example for this dipole moment. Consider the tetraatomic molecule, for example, BF3. Okay, the dipole moment, its dipole moment is 0. Its dipole moment is 0. So thou BF bonds are oriented at an angle of 120 degree to one another. So B, this is F, F, F. Okay, so there is a 120 degree. This is how we representing as I explained just now. Okay, so here what happens, in between them 120 degree, 120 degree, 120 degree. Okay, so there are oriented at an angle of 120 degree to one another. The three bond moments gives a net sum of 0 as a resultant of any two is equal and opposite to the third. So like this it is giving, so it is equal to 0. Okay, so this is the figure. This is about the bond dipole and this is the total dipole moment. Dipole moment. Okay, and next is uh, just as all the covalent bonds have some partial ionic character, the ionic bonds also have some partial covalent character. Okay, the partial covalent character of ionic bonds was discussed by uh, Fajans in terms of the following rules. Okay, some covalent bonds have some partial ionic characters. Covalent bonds having some partial ionic character, like the ionic bonds, they are having some partial covalent character. Some both are partial. Okay, it is having some partial covalent character. Okay, so the partial covalent character of ionic bonds, what is partial covalent character of the ionic bonds? This can be in terms of the following rules. It can be discussed. The first one is, the smaller the size of the cation, the larger the size of the anion. First one, the smaller the size of the cation and larger the size of the anion. Next, the greater the covalent character of ionic bond. So the greater the covalent character of an ionic bond. Okay, so this is the first thing. When there is the smaller the size of the cation, larger the size of the anion, the greater the covalent character of an ionic bond. Next is, greater the charge on the cation, the greater the covalent character of the ionic bond. The greater the charge on the cation and the larger the size of the size of the anion, greater greater the charge on the cation. Okay, so greater the covalent character of the ionic bond. Sorry, this is anion. Okay, uh, it is cation, the greater the covalent character of the ionic bond. Okay, so next one is third one. The cation polarizes the anion, pulling the electronic charge towards itself and thereby increasing the electronic charge between the two. Okay, so these are the three. I will write here. The cation polarizes the anion, pulling the electronic charge, pulling the electronic charge. Okay, electron pulling the electronic charge towards itself and thereby increasing the electronic charge between the two. Okay, so these are the some points and rules which is explained in terms of Fajans. Okay, so the next, I think you have understood this one. Next, this is the dipole moment of selected molecules. Okay, so ab square, ab3, ab4, these are the examples for those. This is this one. Okay, so these are the examples. Next, this is about the dipole moment. Okay, and this is the geometry. These are linear, some bent and trigonal pyramid, and there are the tetrahedral. Okay, so this is about the polarity of bonds and also dipole moment. Next, here, next concept is the valence shell electron pair repulsion theory. Okay, here I will explain you each and everything about the valence shell electron pair repulsion theory. The first here, the some of these are the postulates I am explaining about. This is also called VSEPR theory. It is telling the shape of a molecule depends upon the number of valence shell electron pairs around the central atom. How many number of pair of electrons present shell, that is bonded or non-bonded. The shape depends on, okay, this shell. Then pair of the electrons in the valence shell repel one another since their electron clouds are negative charge. We know that like charges, they are repel each other, so like that they are repelling because all the electrons having the negative charge, that is only they are saying. Next one is, these pairs of electrons tend to occupy such positions in space that minimize repulsion and thus maximize the distance between them. These pair of electrons tend to occupy such positions in space that minimizes the, in see here, this is the nuclei. Okay, this is the orbital where the number of pair of electrons are present. So these are called the shape of the molecule. It depends upon the shared pair of electrons. Okay, the first one. Then pair of electrons in the valence shell, they repel each other because of the negative charge present on the electrons. These pairs of electrons tend to occupy the position in space that which minimizes the repulsion. They occupying the space and also where this the distance maximizes the distance between them, okay, from the nuclei. Next, so this is the VSEPR theory, three postulates, and the next one is the valence shell is taken as a sphere with the electron pairs localizing on the spherical surface at maximum distance from one another. So this is the spherical shape which is in right. So where the valence shell, this is taken as a sphere with the electron pairs, number of electron pairs on the spherical surface, they are present at a maximum distance from one another. There is a maximum distance from one another. Next, a multiple bond is treated as if it is a single electron pair and the two or three electron pairs of a multiple bond are treated as a single super pair. Multiple bond is treated. There are not single bond, two bond, okay, but multiple bond is more than two. So that is treated as if it is a single electron pair and the two or three electron pair of a multiple bond are treated as a super pair. Okay, and this is treated as a single superpair where two or more resonance structures can represent a molecule. The VSEPR model is applicable to any such structure. Okay, when two or more resonance structures can represent a molecule, the VSEPR model is applicable to any such structure. So this is the postulates of the VSEPR theory. And in geometrical shapes of molecules in which the central atom has no lone pair, molecules in which the central atom has one or more lone pairs. So and you should know the repulsive interaction of electron pairs decreases. The repulsive interaction in the order of electron pairs, it is decreases in the order. This is lone pair, lone pair, lone pair and bond pair, bond pair, bond pair. Okay, so this is the repulsive interaction where it is decreases in the order like this. Molecules in which the central atom has no lone pair, and this is when the atom have only bond pair. And so this is about the interaction, and this is the 2 points are some for the prediction of geometrical shapes of molecules with the help of, if you are identifying the molecules shape, the VSEPR theory, it is divided the molecules. VSEPR theory divided the molecules into two categories, that is molecules in which the central atom has no lone pair and they are having the central atom has one or more lone pairs. Okay, next this is the geometry of molecules in which the central atom has no lone pair of electrons. Okay, so they are having no lone pair of electrons here. Okay, number of electron pairs, this represents this column, and this is the arrangement of the electron pairs, and this is the molecular geometry, and this is the example. Okay, and this is also same. And the next thing is molecules in which the central atom has one or more lone pairs. This is the example for that. Next is concept is valence bond theory. Okay, so what happens in valence bond theory?